Everyone, I'm Julia, the chemistry tutor, and today I am going to talk about acid-base titrations. Okay, so let's get started. So a titration is when you use like a solution or solid, okay, a solution of known concentration, and we use molarities on these, or a solid of known mass. Okay, and we use those to determine the concentration of an unknown, typically solution. Okay, not always. Okay, and acid-base titrations is going to be of a solution, but there are a lot of types of titrations out there. Today, we're going to talk about acid-base titrations, but there are precipitation titrations where you're precipitating out a solid during the titration to see, like maybe precipitating out calcium with a hydroxide ion to see how much calcium is in a solution, the concentration of calcium. So there are a lot of different types of titrations. You can do a potentiometric titration to see how much potential, how much electrode potential is going on when a reaction happens. There are a lot of different types of titrations. Today we're going to talk about acid and base titrations. And so you're going to use a known concentration of an acid or a base. Same here with solid known mass of an acid or a base. In this case, it's going to be a base because all of our acids that I talk about are aqueous. So solid mass of a base. Okay, and we're going to determine the concentration of an unknown acid or base. Okay, and all a titration is we are reacting an acid with a base. Okay, and so it has what we call a burette. And you guys have probably seen this. Okay, it has a burette and it has this little tip and this little handle that you turn. It's called the stopcock. And this is graduated, so you know the marks along here. Okay, and you have a solution down in here. Typically, well, you can know either one of them. You could know what's in the burette, or you could know what's in the flask, either way. And you're going to take measurements, volumetric measurements, and see what volume it took for that to turn the color it needed to turn in order to know this reaction is done. And so what we do is we use an indicator that changes color at certain pHs, specific pH, and different indicators turn colors at different pHs. It just depends on your indicator and what pH you're testing for. Okay, but when that turns the different color, let's say I'm reacting sodium hydroxide is in my burette and hydrochloric acid is in my flask, and I'm doing this acid-base reaction. Okay. When it is exactly neutralized, like when you have one drop more, so you have this in the flask, when you have one drop more of the sodium hydroxide, just a tiny bit more, now it's going to be basic because you've used up all of your acid and you're just putting base in there and you're going to get a color change. So you're going to know when the color changes of your indicator in your flask that your titration is finished, and that's when you read the burette. Okay, but I'm not going to talk anymore about what a titration is. I'm sure your instructor has talked about that, or you can go Google it, look at a video on YouTube about what titrations are. Okay, but what it is we've did this when we did solutions. We actually already did the calculations for titrations when we did solutions, right? Because on our little map, we can go for, no, you know what? I'm not even going to talk about the map. I'm actually just going to move into some titration calculations, and you will see we have already done them. Okay, so we're just going to head straight into calculations here. Okay, so what do I have here? If it takes 25 milliliters of that molarity sulfuric acid, so as we're reading that right now, we know that's a conversion factor, right? Because molarities are conversion factors. It means that many moles of sulfuric acid per every 1 liter. Or remember, when we do molarity, let me pop over here real quick, right? If I had a 4.3 molar hydrochloric acid, we could say that's 4.3 moles of hydrochloric acid per 1 liter, right? If we're calculating molarity, it has to be liters. But we could also say it's that many moles of hydrochloric acid in 1,000 milliliters, right? Because 1 liter and 1,000 milliliters are the same. Okay, so when we're doing titrations, we're always working with milliliters. So I always see my molarities as 1,000 milliliters. If your instructors don't allow that, you'll have to convert from milliliters to liters. Okay? Okay, so that's a conversion. So I have two numbers that are not conversion factors, and we're asking for the molarity of the calcium hydroxide. So first of all, they told us that a reaction happened, right? So we have to do a balanced equation every single time. So sulfuric acid reacted with calcium hydroxide. It's a double replacement reaction, neutralization. I'm going to get calcium sulfate and water. If I balance that, I get 2 waters. Okay, and if you're struggling with any of what I just did there, go back and watch my videos on nomenclature, balancing equations, all of that. Okay? Okay, so we have 25 mils of this and 10 mils of this. Okay? So our question is molarity of calcium hydroxide, and molarity means moles per liter, and that's moles of my calcium hydroxide per liter of that calcium hydroxide. Okay, that's what I'm looking for. So because we have a top and a bottom in our question, we have to have a top and a bottom in our starting place. Okay, well, the easiest one to find is always the bottom one. Your volume of what you're looking for is always given to you. So that goes on the bottom. We know we want our calcium hydroxide on the bottom. So our other chemical goes on the top, the 25 milliliters of the sulfuric acid. Give myself some space here. Okay, so we're just going to ignore the bottom for right now. Pretend the bottom isn't even there. Okay, I need to convert my milliliters of sulfuric acid to moles of calcium hydroxide. Okay, so remember when we did our stoichiometry map, right? Volume of one chemical. Right now we know how much calcium hydroxide. Oh, sorry. We know how much sulfuric acid we have. We know its molarity to get to moles. We have a balanced equation to get to moles of our calcium hydroxide. Okay, so we're just using our map. We're using what we already know, what we already learned with solutions. Okay, so in order to cancel my milliliters of sulfuric acid, I'm going to use my conversion, my molarity. So because it's two different chemicals, right, we have to cross that mole river. And as soon as you get to moles, it's where you cross the river. And in my balanced equation, I have 1 mole of sulfuric acid to 1 mole of the calcium hydroxide. So we want sulfuric acid on the bottom to cancel. So we're at moles of calcium hydroxide on the top, which is what we want. So now we're going to convert that bottom. I need to turn my milliliters into liters. Milliliters is on the bottom here. So we'll put it on the top over here. Remember, you don't have to be next door to cancel. You just have to be top and bottom. Liter So my milliliters cancel, and I'm left with moles per liter, which is what I'm looking for. And when I do that calculation, I get 3.05, and that is big M molarity, calcium hydroxide. And that is exactly what I got on my calculator is 3.05. And I've got 3 sig figs here, 4, 3. Okay, so we're going to go with the 3 sig figs. So 3.05 molar calcium hydroxide. Okay, so on a titration, you can calculate the molarity. Remember when we did dilutions and we had M1, V1, M2, V2? And I said if you're given 2 molarities and a volume, or 2 volumes and a molarity, and it's only one chemical, that's a dilution. Okay, so do you see we're given 2 volumes and a molarity, but it's 2 different chemicals. So that is not a dilution. A dilution is specifically only one chemical. Okay, so now let's look at this next one. So what volume of this, so we know that's a conversion factor, 0.65 moles of my sodium hydroxide per, and we're talking about milliliters here, so 1,000 milliliters. Okay, so what volume? So we're looking for milliliters. And sodium hydroxide, and we've got another conversion factor here. Okay, remember our molarities are always conversion factors. So we only have one number, not a conversion factor. That's going to be our starting point. Okay, and it told us that 2 chemicals reacted. So we need a balanced equation. Sodium hydroxide with hydrochloric acid. Double replacement reaction. And it is already balanced. So we only have one thing in our question. How many milliliters? So we're only going to have one thing in our starting place, and that's going to be our number that is not a conversion factor. So we'll start with that 20 milliliters, and that is of the hydrochloric acid. Okay, so now I'm going from volume of one to volume of another. Oh, I want to be back here. So on our handy dandy map, we are going from volume of one to the volume of the other. So we need a molarity, which they gave us, a balanced equation, which we just did, and another molarity, which they gave us. So we have all of our information. Okay, so first we need to cancel that milliliters of hydrochloric acid. So we're going to use the conversion factor of hydrochloric acid, its molarity. So 1,000 milliliters of that hydrochloric acid is 0.275 moles of it. My milliliters cancel. Now I'm at moles. As soon as you get to moles, that's where you cross that mole river. So we go to our balanced equation, and we have 1 mole of the hydrochloric acid to 1 mole of the sodium hydroxide. But we want to know volume of sodium hydroxide, so now we're going to use that molarity with the moles on the bottom to cancel. And the milliliters on the top. And those cancel, and we are at milliliters of sodium hydroxide, which is what we're looking for. Now we just do that calculation. And I get 8.4615 and some numbers. And let's see, I've got 3 sig figs here, 3 here, 2 here. So we're going to go with 2 sig figs in our answer. So 8.5 milliliters of that sodium hydroxide was needed. So on titrations, you can calculate a concentration like we did in the one above. And the one above, because we had a top and a bottom in our question, we had a top and a bottom in our starting place. On this one down here, we only had a top in our question. We only had a top in our starting place. Okay, let's look at the next one. So we're considering the reaction between barium hydroxide and water. Oh, okay, so this is just calculating the concentration. Okay, so if we look, we're just putting barium hydroxide into water. We're just dissolving it in water. Okay, and it wants to know what is the molarity of the barium hydroxide. So how many moles of barium hydroxide per liter of the barium hydroxide? So we've got a top and a bottom. So we need 2 things in our question. Okay, and we're going to assume it's that much solution because we can't add milliliters and grams. Remember, with molarity, we assume that's the amount of solution. If that were a percent, we would have to add our water to our solute to get the total solution. But with molarities, assume your water is your volume of solution. Okay, and so this is actually that many milliliters of the barium hydroxide. Okay. So we want our volume on the bottom. So we put the 250 milliliters of the barium hydroxide on the bottom and our 9.760 grams on the top. Right? Remember, because we know we want volume on the bottom, we put our volume on the bottom. Okay, now it's just a matter of converting our grams into moles. So grams to moles, right, is the molar mass. And so let me add that real quick. And I get 171.35. Total. So we are at moles on the top. Now we just need to convert those milliliters into liters. And our moles cancel, and we are at, oh, sorry, our milliliters cancel. Our liters do not cancel. So we are at moles, which did not cancel, per liters, which did not cancel. Sorry about that. Okay, so now we just calculate that. And I get 0.227837 and some numbers. I've got 4 sig figs here, 4 here, 5 here, so I'm going to go with 4 in my answer. So 0.2287 molarity of the barium hydroxide. So that one was not a titration problem. That one was just calculating your molarity. Okay, but recognizing when we're calculating molarity, it has to be in liters. So up here, we had to convert that to liters. When we're using it as a conversion factor, that's when you can see it as 1,000 milliliters. All right, let's look at what our next problem is. Okay, so we have, okay, so I have this many milliliters of the solution to reach the endpoint in a titration, 25 nitric acid. What is the molarity of the nitric acid? And this is a B, so this solution is this solution they're talking about. We have the 0.2287 moles of barium hydroxide per 1,000 milliliters of barium hydroxide. That is our molarity of that solution. Okay, so nitric acid solution. So we want to know the molarity. So how many moles of nitric acid per liter of nitric acid? And because they told us a reaction happened, we need a balanced equation. So barium hydroxide with nitric acid. Double replacement reaction makes barium nitrate and water. Okay, and we are balanced. Okay, so we have a conversion factor and we have two volumes given to us. Okay, we have a top and a bottom in our question. So we need a top and a bottom in our starting place. We know we want the volume of nitric acid on the bottom. So we're going to put the volume of the nitric acid on the bottom. Okay, and our other number goes on the top. Okay, so when you're doing these titrations, when you're calculating that molarity, the bottom is always the chemical you're looking for. The top is the other chemical. But the easiest way to remember it is that you always want the volume on the bottom of what you're looking for. So find the volume of what you're looking for in your problem, put it on the bottom. Your other number goes on the top. Okay, so ignore the bottom. We're going to convert the top. I need to go from milliliters of one chemical to moles of the other. So we know we're going to have to do cross that mole river, right? Do the stoichiometry. So we have to get to moles. And so we're going to use our molarity they gave us to cancel those milliliters of barium hydroxide. So milliliters of barium hydroxide cancel. You're at moles. As soon as you get to moles, you got to cross that mole river using your balanced equation. 1 barium hydroxide to 2 nitric acids. So 1 mole of my barium hydroxide to 2 moles of that nitric acid. So we're at moles of nitric acid on the top, which is what we want. So now we're going to convert these milliliters into liters. Milliliters on the top over here to cancel. Milliliters on the bottom. Those milliliters cancel, and you're left with moles per liter, which is what you're looking for. Now we just calculate that. And I get 0.211501 and some other numbers. I've got 4 sig figs here, 4 here, 3 here. So we're going to go with 3 in our answer. The 5 will round the 1 up, so 0.212 molar nitric acid. So they might make you calculate first the known concentration of the one that you're using to figure out the concentration of the other. Because remember, titrations are using a known concentration. So like here, I knew this concentration to figure out the concentration of another. Or you can know both concentrations and figure out a volume. We can make you calculate your concentration of the known and then use it in a titration. Okay, so let me just look here real quick. Ooh, we can use it in gas laws. Okay, that's not what I was looking for. Okay, so I'm going to change this question a little bit. I'm going to call this 2.645 grams of that to show you that you can use solids in these also. Okay, so we've got that volume of HF and that many grams of calcium hydroxide. So we want to know the molarity of the HF. So that is how many moles of HF per liter of HF. Okay, so we know we want the volume of it. So by the way, I've not been given any conversion factors up there, right? There's no molarity. Okay, so I did not pull any conversion factors out, but I did say a reaction happened. So we have to do a balanced equation. That is a double replacement. Calcium hooks up with fluoride, H with OH. I need 2 of those and 2 of those. Okay, so we have our balanced equation. We know we want the volume of hydrofluoric acid on the bottom. So we're going to put the volume of hydrofluoric acid on the bottom. So we're 35 milliliters of hydrofluoric acid on the bottom and our other one on the top. So 2.645 grams of the calcium hydroxide on the top. Okay, so we're talking about 2 different chemicals, right? I need to get from grams of calcium hydroxide to moles of HF. And remember, to get from grams to moles, we know we got to cross first we have to cross that mole river. So first we have to get from grams to moles. Okay, and that is using molar mass, correct? So if I add up the molar mass of calcium hydroxide, I get 74.10. So 74.10 grams in 1 mole. We want moles of the hydrofluoric acid. So now is where we cross that mole river. 2 hydrofluoric to 1 calcium hydroxide. So the 1 calcium hydroxide on the bottom to cancel. The 2 moles of hydrofluoric acid on the top. So I'm at moles on the top, which is what I want. Now I'm going to convert that milliliters into liters. So 1,000 milliliters on the top over here to cancel to the 1 liter. My milliliters cancel. And I am left with moles per liter, which is what I'm looking for. So now I just calculate that. And I get 2.0397 and some numbers. And I have 4 sig figs here, 4 here, 4 here. So we'll go with 4 in our answer. 7 rounds the 9 up, which rounds the 4 up. So I'm going to call that 2.040 molar of the hydrofluoric acid. So that's titrations. And you saw on this one up here, because we started with a volume, I know this is very messy, maybe a little bit hard to see. Let me change my color. Okay, because we started with a volume, we used a molarity right there. Okay, that is a liquid-liquid aqueous titration. But down here, I started with a solid. Okay, so because I started with a solid, I needed a molar mass here instead of a molarity. Okay, if we go back to that little map, if you're starting with an aqueous solution of something, then you're starting here and you need to use molarity. But on that last one, we were starting with grams, so we used a molar mass instead. Okay? Just depends on what they give you, how it is that you're going to get to moles. And that's pretty much titrations. I don't think that I really have anything else to say about titrations. Okay, this is calculating your volume. Okay, so, all right, let's do this one. Yep, let's do that one before I call it a day. Okay, so now we have a gas law involved with the titration. Okay, so we've got a volume and a molarity. So I know I have 0.1817 moles of that hydrochloric acid. And this is in milliliters of the hydrochloric acid, so I'm going to put that in milliliters. So there's my conversion factor. Volume of CO2. Okay, so we are reacting hydrochloric acid with sodium carbonate. Okay, this is a double replacement reaction. Okay, I'm going to leave it like that to balance it. Okay, so now we're balanced. Okay, but I don't know if you recall, this is an unstable acid. It always breaks apart into water and carbon dioxide. So there's my carbon dioxide in this equation. Okay. Okay, so we've been given one pressure, one temperature. It's asking for the volume. So we've not been given two of anything. So we know we're going to be looking at PV equals nRT. So my P, my V, my N, and my T. My pressure is the 722. But remember, for the ideal gas law, we have to be an ATM. So let me calculate that real quick. I get 0.95, but we need 3 sig figs on that, so 0.950. My volume is what we're looking for. My temperature was the 28 degrees plus the 273. There's no decimal places on that 28, so I'm not going to use the 0.15. So that's 301 K. Okay, so we know, don't know what is going on there. Okay, so that number of moles has to come from somewhere else. And that is coming from our titration. Okay, so we want to know, this is going to be how many moles of the CO2. Okay, and I'm going to start with my 28 milliliters of the hydrochloric acid. Right, and we know we're starting with that because these numbers are for the gas law. So we're not using those for this. Those are for the gas law. Remember, your moles comes from somewhere else. So I need to get from milliliters of hydrochloric acid to moles of CO2. So I'll use that molarity that they gave us. Right, they gave us the molarity. Okay, but we want moles of the carbon dioxide. So 2 of the hydrochloric acid to 1 of the carbon dioxide. Okay, so now we've got, oh, it was 28. Okay, so I get 0.0025438. And if we're doing sig figs here, we want 4 and 4. So 4 in my answer. So I've got 0.00254 moles of CO2. So now I can do my gas law. So PV equals nRT. We're solving for V. So we're going to move P down to the other side on the bottom. So we know our moles. I don't have enough room here. Let me go down below. So we know our V is going to equal to our number of moles times our R times our temperature divided by our pressure. And our moles cancel, our ATMs cancel, our Ks cancel, and we're left with the volume that we want there. So now we just calculate that. Okay, and when I calculate that, I get 0.066144, and I've got 4 sig figs there, 4, 3, and 3. So I'm going to go with 3 in my answer. So 0.0661 liters of CO2. And if it had asked for milliliters, right, we would just convert that into milliliters. If it had asked for milliliters, and there'd be 66.1. Okay, so we can use molarity. I mean, these are kind of titration problems, but not really. I mean, we can calculate concentrations, like we could have calculated the mass of sodium carbonate. Now, going back from my milliliters of this through a gas law to moles of that, and actually use the moles of that. And so there's a lot of different things you can do with this. I'm not going to go any further into that. Okay, but basically it's just using molarity as a conversion factor. That's titrations. I really don't think that I have anything else to say today about titrations. So have a great day.